Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, my wonderful students. I want to take this time to welcome you again for yet another session of interesting learning on TV. My name is Teacher JB, and I'm sure you have seen me for quite some time. And so today, I am going to be learning together with students of Senior 3, Physics. Very interesting subject, isn't it? Yeah, I think it is interesting. And so we are still on unit number 5, which is about heat transfer and quantity of heat. We are still there. Quite a wide topic, but we shall finish. And for today, we shall be looking at experiment to measure the specific capacity of a liquid. That's the only thing we want to be looking at. It might look very small when you look at the title, but it is not small. Some people feel it is hard, but it is not hard. Just remain interested the way you are. We are going to learn this together very nicely. And so, by the end of today's lesson, after these 30 minutes or so, you should be able to perform and, of course, describe. You can't perform an experiment if you can't describe. So we should be able to perform and describe an experiment to measure the specific heat capacity. You see, when I write SHC, I'm just using symbols. They are not standard. I didn't want to take a lot of space. So specific heat capacity of a liquid. And then we should be able to use the results from such an experiment, may not be only this, to be able to find the specific capacity of a liquid. And we shall also see, from this experiment, we can also find the specific capacity of other materials. So that's what we are going to be doing basically today. Now, before we start, I want you to remind yourselves of what we were looking at last time. Remember the last time around we were here? We had some devices here, and I want to believe that they are familiar. For instance, this. You remember this? We looked at it last time. If I open it up, it's a calorimeter. We talked about that. So inside you have a heating element. So this is electric heater, and that is a calorimeter. That's what it looks like. Kind of like a flask, the one you have at home, right? Yes, so we call this a calorimeter. Now, last time we showed you how you can use this kind of calorimeter to find the specific capacity of a solid. And I remember the solid that we used. Some of you might have forgotten. I still have my solid here. I kept it. It was this one. So, today, we are not going to look at how to determine the specific capacity of a solid, but rather how to determine the specific capacity of a liquid. So that's what we are going to look at today. Right. So, borrowing from what we looked at last time, the statement we looked at was heat produced or supplied by heater must be equal to heat absorbed. Heat absorbed by the solid. Do you remember that statement? And also we went ahead and said the heat supplied by a heater is given as VIT. And so VIT is equal to mass, which is mass of the solid, times specific capacity of the solid, then times temperature change, where we said it is the higher temperature, which is theta 1, minus the lower temperature, which is theta 0. Some people use theta 1 and theta 2. No problem. Some people even use T1 and T2. No problem. You should only know, why am I using theta 1? Between theta 1 and theta 2, which one is bigger and which one is smaller? That's the most important thing. Okay, so we looked at this relationship last time, but we were looking at specific heat capacity of a solid. And so from this formula, if you make C the subject, okay? If you make C the subject, you remember we did that? C will be equal to VIT over M into theta 1 minus theta naught. So knowing all those, we were able to find the specific capacity of a solid. And so, my dear friends, my dear students, today, as I told you, we are going to concentrate on determining specific capacity of a liquid. And for us here, the liquid we are interested in is water. I'm just trying to increase the amount of heat so that our water can boil quite quickly. So the liquid we are interested in here is water. So we shall determine the specific capacity of the water. So let me introduce to you familiar and non-familiar apparatuses. There's this one. I don't want to call this non-familiar. We have used it before. Just remind yourself, what is it called? A thermometer. Good. Remember, I'm removing it from hot water. I just want to cool it down. I don't want it to be hot. So I'm trying to cool it down. Okay? You will even see that the scale begins to reduce. I just want to cool it down. Nothing technical there. Okay. The second item, which could be non-familiar to you, is this. This one is called an electronic balance. It is used for measuring mass. That is what we use it for. Okay. This, you can't say it is non-familiar. This is familiar. You have seen it before, especially if you attended our lessons last time. This is called a calorimeter. It is made of copper. It has the outer case and the inner tin. If I remove the inner tin, just for curiosity, look at what is inside. Right here. You see, there's some lagging inside. It looks like a small piece of a blanket. For lagging, we talked about last time, it is to reduce heat loss. And the most important part of the calorimeter is actually this. This is important as well because it helps to prevent heat loss, to reduce heat loss. But this is the heart of the thermometer. I mean, the calorimeter. Not thermometer, calorimeter. Okay. Is there anything that you feel is strange here? I guess no. This is a calculator. My laptop, there's nothing else new. Okay, let's go ahead. Now, experiment to determine the specific heat capacity of a liquid using the method of what? Mixtures. So we are going to determine the specific capacity of a liquid using the method of mixtures. That's the main thing we are doing today. And so let's look at the diagram. Just above the diagram, you have got apparatuses that we need to use. I have introduced most of them to you. Electronic balance, which is this one. You have seen it. Thermometer, right there. You have seen it. Metal block. Okay. Metal block is here, right inside there. I'm using this thread so that I don't touch the hot water, okay? We are dealing with hot water, so you have to be very careful. You don't want to burn yourself. So that is my metal block, and the red stuff is a thread. Then you have water, of course, a lot of water around here. You will see why we are using it. A beaker, we have it there. A stirrer. A stirrer comes with a calorimeter. It's right here. You can, as a layman, you would call it a spoon, you know? Like a spoon, you use it for mixing your tea with the sugar. Then calorimeter, heat source, we have our Bunsen burner, and a tripod stand. This is a tripod stand. Okay, so the diagram is like this. Here we have got a beaker which is being heated, and inside there is a solid block. Our solid block is right inside there. Are you able to see? Right inside there. The only thing we don't have in this diagram is a thread, but the thread is right there. Then in the second diagram, we have a calorimeter. And you still have a metal block. Then we have a stirrer. Then we have a thermometer inside there. And then there's a lid. So that's how our diagram looks like. Let's go to the procedures. Okay? Let's follow this nicely. Let's follow this nicely. Let's go to the procedures. Some students, with my experience of helping students find such experiments very hard to perform. But I want to believe that from today, after this lesson, you will be able to do that. Okay, let's go to the procedures. Procedure number 1, measure the mass of the solid block provided. Measure the mass of the solid block provided. And what are we going to use to measure the mass of the solid block? We are going to use the electronic balance, which is this. As you can see, the scale is 0, indicating 0 grams. So I'm just going to transfer and put it there, okay? If you are not seeing it very well, I am going to do like this so you can, but you see it is very sensitive, so when I adjust, it changes. But right now, the tare value is 0 grams, so no mass. So I'm going to remove this and try to get its mass. Okay, I'm going to put it on there. Remember, it is hot, so you have to be careful it doesn't burn you. Right now, I'm seeing 101.34 grams. 101.34 grams. 101.34 grams. I will try to make you see it better. Let me just record it here. We are saying this mass is ms, which is equal to 101.34 grams. That is ms. I was trying to tell you that it is very sensitive. If you touch it slightly, it changes. I think you can see it is changing because this device is very sensitive. But from here, my screen is reading 101.34. Okay. Let's go ahead. Remember, after measuring, I want to take this back so that it is in the water. I'm going to take it back. So we have our ms. Let's move ahead. The next procedure, heat the solid in the water until water begins to do what? To boil. Okay. That's why we were very clever. We started boiling before so that we don't waste a lot of time. And so our water is practically boiling. The most important thing they are saying there is we should measure, you see, measure the temperature theta 2. Theta 2. Measure the temperature theta 2. So I'm going to put my thermometer back inside there. Remember, right now, I am removing it from cold water, so we should see the mercury thread rising. Okay. Do you see it rising? All right. So it should continue rising until we attain a constant temperature. So let it continue rising. Right? Okay. Let it continue rising. I'm going to give it about 10 seconds so that we can get the final temperature. And as we are we are preparing to take the value of theta 2, let us look at the next procedure. The next procedure says, pour some mass MW, okay? Some mass MW of cold water at temperature theta naught into the calorimeter, okay? Pour some mass MW of cold water at temperature theta naught into the calorimeter. All right. Let's check what is happening here. I want it to boil, but not yet reaching the point I want. So let's first continue with the other procedure. Let's continue with the other procedure. We'll come back there. Now, in this calorimeter, we have got some water. And this is the water. It's right inside here. Okay, this is our stirrer, and the water is inside there. So what am I going to do? They want us to measure and find the mass of water, MW, in the calorimeter. So what do we do to find the mass of this water? Okay. I'm going to transfer the water in the calorimeter. I will transfer it here. Do you see that I've transferred all the water in the calorimeter? Okay? Now, I am going to put this on our electronic balance. And then we take the reading. And then we take the reading. The reading right there is 186.21 grams. So, this is mass, remember, of the beaker plus water. Mass of the beaker plus water. Let me read it again so we can see. It is 186.21 grams. 186.21 grams. That is mass of the what? The beaker and water. So what are we going to do to get the mass of the water alone? To get the mass of the water alone, I'm going to remove this water and pour it back into the calorimeter. And I need this inside the bigger can. So I've taken back the water, remember? And this is the starter, I'm taking it back inside. So if I want to get mass of the water alone, what am I going to do? I'm going to check that the reading is at 0 grams, then I place the empty beaker back on top. And that is what I've done. The empty beaker back there. It is giving me a mass of 101.59 grams. So, this is mass of beaker only. Okay? Don't want to forget that figure. It's 101.59. 101.59 grams. Remember, this is beaker plus water. This is beaker only. So it means mass of water only, because that's what they want us to get, is going to be mass of beaker plus water, which is 186.21 grams, minus mass of what? Of beaker only, which is 101.59 grams. Do you follow that? We want mass of water only. So I'm going to press my calculator. I hope you have yours too. So this is 186.21, okay, minus 101.59. What do I get? 84.62. So I'm getting 84.62 grams. So we are done with mass of what? Of water in the calorimeter, which is this one. Then they're telling us, measure also temperature theta naught in the calorimeter. So we have the same water. It is still here in this calorimeter. We want to measure its initial temperature. So I'm going to put the thermometer there. You need to look at the scale very well. Check if you can see the scale very well. Tell me yes if you can see the scale very well. Okay. Do you see the scale very well? Tell me yes if you do. Okay. Right. Let me also take my reading. To avoid parallax, I need to look at it at an angle of 90 degrees. So let me take mine. I will give you a chance to take yours also. So let me take mine. This is giving me 26 degrees Celsius. Okay? Can you also check for yourself? $26. Okay? All right. So let us record that. So we shall come here and say theta naught is equal to 26 degrees Celsius. So we are done with that. Let's move ahead. Can we come to this one? Record the specific heat capacity of the material of the calorimeter. That one we are just going to record it. And for now, I will just tell you what the value of the specific capacity is. So the specific capacity of the material, our metal, is equal to 462 joules per kilogram per Kelvin. Right. Let's go ahead. because your teacher will give you that. Remember, it's not what we are looking for. We are looking for specific capacity of water. Let's go ahead. Quickly, remember we were here heating the solid until theta 2. We didn't get theta 2 because we wanted it to first of all boil. Do you think it has boiled? Yes. So can we now go ahead and get theta 2? I believe so. So we'll put our thermometer there. Again, you should watch the scale as it rises. As it rises. Okay. Is it rising? Yes, it is rising. It's approaching 90 according to me. And it is still rising. 93, it is still rising. For you want to look at it alone, I also need to look at it, okay? Thank you. Okay, thank you. Okay, continue looking at it. I'm not saying you should stop. Continue watching it. All right? When you go back to school, you should do the same thing. All right. This is 95. Coming to 96. All right, let's stop there. We don't need the water to boil at 100. Let's stop there so that we can move faster. Okay, okay. So, are you able to see it for one last time? Okay. So right now, it is 96 degrees Celsius. Remember, 96 degrees Celsius. So I will record it quickly as theta 2 is equal to 96 degrees Celsius. Now the thing is, they are telling us here, quickly transfer the hot water into the solid in the calorimeter. So quickly, so we have to do it very quickly. I'm trying to do it quickly. I remove my thermometer from here. Very quickly, I have the calorimeter right there. I transfer it there quickly, and I should put the lid back. And what are they telling us to do? To stir. So stirring means I should mix. And as I mix, you should see what will be happening to the temperature of the water. Remember, it was 96. Okay? So as I continue stirring, you should be looking at what is happening to the scale of the thermometer. Right now, it is somewhere around 38, 36, and it is still falling. So I continue stirring. Because what have I done? If you remember from thermal equilibrium, I am mixing hot metal with cold water. So the hot metal is going to lose heat to the cold water, and the cold water will gain heat until the two of them come to the same temperature. So right now, I'm looking at a temperature of 35 degrees Celsius. I will continue stirring for a little while. Let me put off my gas so we don't produce any more heat. Okay. Okay. Right now, I can see it is about 34 degrees Celsius. Okay? 34 degrees Celsius. So let us record that at our theta 1, the final constant temperature. So we shall come here and say theta 1 is equal to, what did we find as our final temperature? Do you remember? Maybe you have forgotten. Do you remember? We got it at around 34 degrees Celsius. So theta 1, 34 degrees Celsius. So coming to part F, use the balance to determine the mass M of the empty calorimeter. Okay, we shall come to that later on. So after getting these values, the statement we should use is, if no heat is lost to the surrounding, then the heat which was lost by this solid, remember, is equal to the total amount of heat which was gained by the water inside the what? The calorimeter. Because they all came to the same temperature. That is what we call thermal equilibrium. And if that is true, it therefore means mc theta, remember this is for the heat lost by the metal, should be equal to mc theta, heat absorbed by the what? the water. Theta 2, theta 1, we have already discovered all of them. Even theta naught, we have discovered it. So everything here is known. And so if you make CW, this one, the subject, we divide this side by MW times change in temperature. If you divide that, then CW will be equal to this, which is the specific capacity of what? Of water. Do you see how you get that expression? And so let us then feed in these values and see whether we can get a specific capacity of water. So CW is equal to mm. Remember, mm is mass of the metal. Mass of the metal. Did you find mass of the metal anywhere? Oh, we didn't do that. So we have to go back and find mass of the metal, which is still okay. So we get our metal right there. Then we determine its mass. So mass of the metal, 102.3 grams. So mass of the metal, 103.2 grams. So we shall put mass of the metal, which is 103.2 times specific capacity of the metal. We already have it here, 462 times change in temperature, theta 2 minus theta 1, 96 minus theta 1. Theta 1 is 34. Then over mass of water. Mass of water is right here, 186.21 times theta 1 minus theta 0. And theta 1 is 34. Minus theta 0 is 26. Okay, let's just compute that very quickly. Let's compute that very quickly. So you have 103. Can you press it together with me? 103. Okay. All right. Let's check again. Down we have mass of water. Okay. Let's check again. Mass of water, MW. Oh, sorry. What I did is I just took the first one. I should have taken the final value. Okay? Thank you. We realized that. So I'm going to remove this. It is not 182. Sorry for that. It is 84.62. Okay. Let's go back to the calculator. So you have 103.2 times 462 times 96 minus 34. I'm getting 2956060.8 over, we have 84.62, I hope you're pressing it, times 34, right, minus 26. We get 676.96. Let's go ahead. So if I divide those two, I get 295,606.0.8 divided by 676.96. So I have 4,366.7. This is joules per kilogram per Kelvin. So what we have got here is the specific heat capacity of what? Of water, which is 4,366.7 joules per kilogram per Kelvin. Now, as we conclude, an experiment like this, the true value is 4,200. But from our experiment, we have got 4,300. Isn't that very close? Yes. There are reasons for this, which is what we are going to discuss next time about ways of improving the accuracy of the what? Of the experiment, so that we can get, we explain why we don't get 4,200. Okay. As we end, I want you to remain with this assignment. You can do it up. The two assignments, I think they are very clear. You can read them and follow, and that is your reference. And I want to thank you again for being attentive. Continue watching our programs until we meet again next time. Thank you.